topic we'll be discussing in this lecture is signal propagation. So let us try to understand the behavior of an radio signal. If you take a wired signal, when the signal is communicating through a wire, it has a proper behavior because the behavior is controlled through a wired channel, and the behavior of the wired communication is predictable. That is, the received power will depend on the length of the wire. As the length increases, the power will decrease slowly. But that is not the case in a wireless communication. In a wireless communication, also, the behavior of the signal is predictable if the channel is vacuum. That is, if the media through which the signal is transmitted is vacuum. But in real life, the media is not vacuum. Actually, the media contains several kinds of disturbances in the form of there may be rain, there may be snow, there may be smog, there may be dust. So all these things will affect the signal. And the signal may have to pass through different objects like buildings, trees, etc. So these objects will also distort the signal to certain extent. Hence, let us try to understand the transmission range of an wireless signal. So the transmission range of a signal, I mean the communication range. Let us understand the communication range of the signal. The communication range of the signal can be divided into the three parts like transmission range, detection range, and inference range. So transmission range represents the, say for example, if this is the sender, say if this is the sender, and the sender can transmit information up to a certain range, in such a way that the receiver can also receive this information with less errors, and also the receiver can communicate back to the sender. So this range, it may be several meters or several kilometers depending on the strength of the signal that is transmitted by the sender. So this range, the first range is called as transmission range. So within the transmission range, the receiver can receive the signal, and also he can communicate back to the sender. So that is what is called as transmission range. The next thing what we have is detection range. So in transmission range, the possibility or the error rate will be very low. So in the detection range, this is the next range. Here the signal will be transmitted, and the receiver will be able to receive these signals. This range is called as detection range. The receiver will be able to detect this signal, but the receiver cannot communicate back. So the distance or the range through which the signal can reach, where the receiver can detect the signal, but the receiver cannot communicate back. So that range is called as detection range. And the next range is inference range. So with inference range, the signal may not be even detected. The next range is inference range. Here, the signal, detecting the signal also becomes difficult. Okay, and the signal becomes more weak because of background noise. So that range is called as interference range. So as the distance increases, the strength of the signal keeps decreasing. Okay, so the first few meters or first few kilometers, that forms the transmission range, and and the next radius and the next circle that forms the reduction range, and the next forms the interference range. In transmission range, the signal can be received properly by the receiver, and the receiver can also communicate back. And there will be few error rate. In detection range, the signal can be detected, but the receiver cannot communicate back. In the interference range, the signal may not be detected. Detecting itself becomes difficult, and a lot of background noise will be added to the signal. Okay. So this is how a typical wireless network behaves. Okay. Or this is how the signal is propagated through an wireless channel. Okay. Yes. Next, we will try to understand the path loss of radio signals. So when the radio signal is transmitted through the free space. That is, it does not have a wired channel for communicating. So it is transmitted through the free space. So how light is getting transmitted in the free space, in the similar way, the radio signals also getting transmitted. In some cases, there may be a straight line of communication possible between the sender and the receiver. When the radio signals were transmitted between the sender and the receiver, if there is a straight line of communication exists between the sender and the receiver, then that is called as LOS. LOS stands for line of sight. LOS stands for line of sight. But always this straight line of communication may not be possible. Okay? But always this straight line of communication may not be possible, and and even if there is and as we already discussed, uh, when the when the radio signals are getting transmitted, it may have to go through different types of disturbance, like there may be rain, there may be wind, there may be fog or snow. All these things will disturb the signal. Okay. Even if there is no such disturbances, even if there is no such disturbances, even if the signal is even if there is no matter between the sender and the receiver, even if there is no matter between the sender and the receiver, that is, if the signal, assume the signal is getting transmitted through the free space, then also there will be some loss. There will be some loss in the signal, and that loss is called as free space loss. That loss is called as free space loss. And the free space loss is given by this particular formula, that is, the received signal will be proportional to 1 by d square. Okay, this is d square. So which means that, so this law is called as inverse square law. That is, as the distance increases, the strength of the signal will decrease. So the received signal will be proportional to 1 by d square, where d represents the distance. Here d represents the distance. So this is called as inverse square law. And inverse square law represents the free space loss. That is, even if there is no media between sender and receiver, there will be some loss in the radio signal, and that loss is given by this particular formula. Fine. If there is some matter exist between the sender and the receiver, then the situation will become more complex, because there are some matter, not medium, matter. If there is some matter exists between the sender and receiver, then the things will become more complicated, because even if there is no matter exists between the sender and receiver, there is the loss is proportional to 1 by d squared. If there is some matter present between the sender and the receiver, uh, then the loss will also increase. Okay. In real time, if you see, uh, the radio transmission has to go through these type of disturbances. It may have to go through air, rain, snow, fog, dust, smog, etc. So all these things will disturb the signal. Fine. Now let us try to understand the, the behavior of radio signal at various frequencies. behavior of the radio signals at various frequencies. Okay. So yes, yeah. So before that, uh, let us understand what is path loss or attenuation. So 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 when the radio signals are getting transmitted over long distances, they, there will be lot of loss. There will be lot of loss, or the signal will get disturbed. Okay. Example is satellite transmission. Example is satellite transmission. So in satellite transmission, there will be there will be path loss. Okay. That is, as the distance increases, the signal strength will decrease. Okay. And now let us understand the behavior of the radio signals with different frequencies. If the frequency is less, if the frequency is less, then the radio signals can penetrate objects. It can penetrate objects like trees or buildings, etc. So long waves, so basically long waves are used for transmitting through submarines. Long waves are used for transmitting information through ocean to submarines. Okay, long waves means the waves whose frequency is less. If the frequency is less, then the waves will be longer. If the frequency is high, then the waves will be shorter. Okay, so long waves are nothing but low frequency waves. Long waves are nothing but low frequency waves. So long waves, you can see long waves or low frequency waves can penetrate objects, whereas high frequency waves will get blocked by objects. Okay, as the frequency increases, as the frequency increases, the waves will get blocked by the objects. That is, it cannot penetrate object. Rather, the object will absorb the signal, radio signal. Okay, example trees. Okay, so that depends on the frequency of the signal. As frequency increases, the signal will behave more like a light. As frequency increases, the signal will behave more like a light, right? Let us discuss some different types of signals with different frequencies. So if the frequency is less than 2 megahertz, then such signals are called as ground waves. Such signals are called as ground waves, and they are typically low frequency waves, and they can follow Earth's surface, and they can propagate over long distance, and they are used for submarine communication. So previously also we have discussed, for submarine communication, low frequency waves are used because they can pass through the ocean. Because they can pass through the ocean. And AM radio, amplitude modulated radio, also uses waves at this particular frequency, less than 2 megahertz. Sky wave. The next is sky wave. The frequency of sky waves are in between 2 to 30 megahertz. The frequency of high waves are in between 2 to 30 megahertz. These waves will get reflected at ionosphere. That is, the ionosphere is one layer of atmosphere. It will get reflected at ionosphere, and again it will get reflected by the Earth's surface. So it will be just getting transmitted back and forth within the Earth's atmosphere. So basically, it is used for international radio broadcast, like amateur radio. For these things, sky waves are used, which works at a frequency of 2 to 30 megahertz. And then we have line of sight, whose frequencies are more than 30 megahertz. Basically, these are used for mobile phone systems, satellite system, cordless phones, or so such devices operate at these frequencies. Okay, so the emitted waves from these devices will follow a line of sight. That is, if there is a line of sight, then these devices will work properly, like mobile phones, satellite systems, or cordless telephones. Okay, so this is about path loss of radio signals. Okay. Next, let us try to understand certain additional signal propagation effects. Okay. That is, when a radio signal is transmitted uh, through the environment, how the radio signal can get disturbed, or what are the different types of disturbances it encounters. So that we will discuss in different headings. The first is blocking or shadowing. So as we have discussed previously, if the frequency of the wave is low, that is, if the frequency of the wave is low, then it is a longer wave. If the frequency of the wave is low, then it can penetrate objects. But if the frequency of the wave is high, then it will get blocked by the objects. Okay, that is called as blocking or shadowing. Because as frequency increases, the radio signal will behave more and more like a light. And these signals will get blocked by walls, trucks, trees, all these objects. Okay, so that is called as blocking or shadowing. And then we'll be discussing about reflection. If the object is large when compared to the wavelength of the signal, if the object is large, so reflection in the sense, if the object is large compared to the wavelength of the signal, like huge buildings or mountains, then then the signal will get reflected. Then the signal will get reflected back, and the reflected signal will not be as strong as the original signal. The reflected signal will not be as strong as the original signal. The signal becomes weak because some energy of the signal some energy of the signal will be absorbed by the object, because some energy of the signal will be absorbed by the object. But reflection helps in transmitting radio waves when there is no line of sight exists. For example, if there is no line of sight between sender and the receiver, then actually in such cases, reflection helps us in transmitting the signal from the sender to the receiver. So this is about reflection. The next thing that we'll be discussing is refraction. Refraction. Sometimes the signal get refracted. So that actually depends on the frequency of the signal, and also it depends on the density of the medium through which the signal passes. Okay. So it also depends on the velocity of the signal, that is the speed at which the signal is coming, and it also depends on the density of the medium the signal passes. So in that case, the signal may pass through the, if it is a relatively a high frequency signal, then the signal may pass through the particular object, but the signal's direction may get changed. The signal's direction may get changed. So this kind of distortion to the radio signal is called as refraction. Okay. The next is scattered. Sometimes the signal may get scattered if the object is in the order of the wavelength, or if it is less than the size of the wavelength, then the signal will get scattered. So here you can see there is a diagram for scattered. So this is a typical example for how the signal is getting scattered. Okay, so scattering happens if if the object size is uh, less than the wavelength, then the signal will get scattered. Okay, whereas if the object size is greater than the wavelength, then shadowing or reflection will happen. So here the signal will get scattered into multiple signals, and these multiple signals will be weak in nature when compared to the original signal, because some of its strength will get absorbed by the object. So that is called as scattering. The next is diffraction. Okay, in some cases, the radio signal will get deflected by some edges, maybe an edge of a mountain or such things, and it get deflected. So this is an example for diffraction. So all these diagrams shows like, so this shows what is shadowing. So in shadowing, the wave get in shadowing or blocking, the wave, the radio signal get blocked totally. There is no reflection, no refraction, nothing. Okay, it is the object just absorbs the signal. Whereas in reflection, the wave get reflected. Okay, the wave get reflected, and the reflected wave will it will not be as strong as the original wave, and it will become weaker. So reflection and shadowing happens if the object size is greater than the wavelength. With refraction, so refraction happens because that refraction depends on the velocity of the signal and the density of the medium through which the signal passes. So in this case, the signal's direction will get changed. Okay. In scattering, what happens in the sense, the signal will hit the object and it will be scattered. It will be scattered into multiple weak signals. Scattering happens if the object size is less than the wavelength of the signal. And the last is diffraction. So sometimes if the object hits some edge of the object, then the wave may get diffracted. Okay. So these are the additional signal propagation effects. Okay. So these are the additional signal propagation effects. Right. And the next topic we'll be discussing is multipath propagation. Okay. So what is meant by multipath propagation? So assume an wireless signal is getting transmitted from a sender and the receiver. So let us, so in this diagram, if you see, you can, let us assume this base station as the sender, and the person who is traveling in this car as the receiver. Okay. So here you can see there is a line of sight exists between the base station and the car, that is between the sender and the receiver. So the signal is received through the line of sight, that is through one path. This is one path. Okay. So this is one path. And also the signal is received by getting reflected from a nearby building. So this is the second path. And also the signal is received by getting scattered by another object. So this is third path. Okay. So here three paths are shown, but in reality, like this, whenever a radio signal is communicated between a sender and the receiver may receive the same signal from different paths, maybe tens or even hundreds of paths. Okay. So that is called as multipath propagation. So that is called as multipath propagation. And because of multipath propagation, what happens in the sense, it will lead to something called as delay spread. It creates something called as delay spread. That is, the signals traveling along the different paths with different lengths are arriving at different times. So that concept is called as delay spread. And sometimes, uh, so generally the delay spread in cities is between 3 microseconds to 12 microseconds. If you take GSM, Global System for Mobile Communication, it can tolerate a delay spread. It can tolerate delay spreads of up to 16 microseconds. It can tolerate delay spreads of up to 16 microseconds. Okay. So, and another issue with the delay spread is, assume assume the sender is sending two different signals. So here you can see this graph. Here let us assume this is the signal 1 which is sent by sender at time t1. Okay. Similarly, the sender is sending some other signal 2. The sender is sending some other signal 2 at time t2. Okay. So basically the sender is sending uh, two signals. One signal he is sending at time t1, another signal he is sending at time t2, right? But due to multipath propagation, these signals may uh, these signals may spill over time. These signal may mix with each other. So that is called as intersymbol interference. That is called as intersymbol interference. So such problems may also be created because of delay spread. Delay spread occurs because of multipath propagation, and because of delay spread, problems like intersymbol interference (ISI) can also happen. Okay, so this is what we already discussed. That is, the delay spread in cities will be about 3 microseconds to 12 microseconds. GSM can tolerate a delay spread of up to 16 microseconds, and the effects of delay spread will make the signal weak, and it may lead to a problem called as intersymbol interference, where the energy intended for one symbol may spill up or mix up with the adjacent symbol. Okay, but the problem with intersymbol interference can be overcome, or it can be compensated if the delay is known. If the delay is known, that is, the signal is coming through different paths, right? So what are the different paths the signal comes, and and what is the delay of each path? If the receiver knows that, then the receiver can perform something called as distortion, compensate distortion. That is, whatever the extent to which the signal has distorted, that he can compensate. Okay. So how it is done in the sense, initially the sender should send a training sequence. So training sequence is some audio message which the receiver also has previously has the same copy of the message. And now when the sender is sending that training sequence, the receiver will observe like in what pattern the training sequence will arrive is arriving. So based on that, the receiver can know the delay from the sender, and accordingly he can perform the compensation. Okay. But this is possible only if the sender and the receiver were fixed. This is possible only if the sender and the receiver are fixed. If the sender and the receiver are fixed, then the intersymbol interference can be avoided by performing compensation. Okay, this type of compensation if the delay is known by using a training sequence. But if the sender and the receiver is moving, if the sender is also moving and if the receiver is also moving, then the things becomes more complicated. So, 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 so ISI and delay spread uh, can be avoided if the transmitters and receiver are fixed. But the problem will become more worse if the sender and the receiver moves. So this is a typical example we all might have experienced in watching or listening to a radio when you are traveling. When you are traveling in a vehicle, the signal you will not get the signal properly. The reason is the receiver is keep on moving. The receiver is keep on moving, so the receiver is keep on getting adjusted to a correct frequency to receive the signal. Okay. So that concept is called as short-term fading. That concept is called as short-term fading. Here you can see the sender is moving. No, at different point of time, the strength of the signal or the power of the signal that the receiver is receiving is varying. So the receiver is keep on adjusting himself uh, to to adopt to the varying channel characteristics. So the receiver is constantly trying to adopt to various channel characteristics. Okay, so that is called as short-term fading. If the receiver is moving at a faster speed, then probably the receiver may not receive any useful signal at all. Okay, and if you take the average received power over time, if you take the average received power over time, so that is represented by this rose color line, so that is called as long term fading. Okay. And long term fading can be compensated, by increasing or decreasing the sender power. If the sender sends at a higher power or at a lower power, depending on the uh, long-term fading experienced by the receiver, accordingly uh, the long-term fading can be compensated. Okay, so that's it about signal propagation. So here we have discussed like how signal is propagated initially. There are three forms of signal propagation. Like there are three ranges: transmission range, detection range, and interference range. These ranges vary with respect to the distance. Then we have discussed path loss of radio signal. Like in free space also, the radio signals will encounter some loss. So which is proportional to 1 by d square. Okay? That is, as the distance increases, as the distance increases, the strength of the signal decreases. So that is given by inverse square law. But if there are other what do you call uh, other matters or in between the communication, then the signal will get even worse. Okay, and then we have discussed the characteristics of wireless signal with respect to different frequencies. So less than 2 megahertz, it is ground waves. These are low frequencies waves which are used for submarine and AM radio communication. Sky waves are between 2 to 30 megahertz, which are used for amateur radio broadcast, international radio broadcast, and line of sights which are greater than 30 megahertz are used for mobile phone, satellite, and cordless telephones. And then we have discussed the various signal uh, propagation effects like blocking, shadowing, scattering, diffraction, all these things. And then we have discussed what is multipath propagation and how multipath propagation leads to delay spread. And because of delay spread, we experience a problem called intersymbol interference. And this intersymbol interference can be compensated if the delay sequence is known. The delay is known by performing a training sequence. So, but this compensation can be done only if the sender and the receiver are fixed. If the sender and the receiver are moving, then the system will experience short-term fading. And the average power over time is called as long-term fading. And long-term fading can be compensated by increasing or decreasing the sender power. So let us stop here. Thank you.